Welcome back to the first year topic, that is atomic structure. The last part of this one is electronic configuration of some elements. Electronic configuration of some elements. In this chapter we consider only the elements up to atomic number 30 or so. Some elements. So, to write the electronic configuration, we have three important rules that we have studied in the previous videos. One is Pauli's exclusion principle, the Hund's rule of maximum multiplicity, but before these two we have that AIEEE principle. AIEEE principle is actually indicating the various energy levels of the orbitals. So, to calculate that energy level, we are using N plus L rule. If N plus L rule is applicable, if two or more orbitals have got the same N plus L values, then we have to use lower N value to study the lower energy. Then we have that Pauli's exclusion principle. No two electrons in an atom can have all the four same quantum numbers. Then Hund's rule of maximum multiplicity says that if equal energy orbitals are available, first we have to make half filling. Only when all orbitals get one electron is, then we have to go for the pairing of the electrons. So by using these three rules, we are writing the electronic configuration. So here we have atomic number, element, then electronic configuration. Electronic configuration. So first let us start with this hydrogen, atomic number 1. We have this hydrogen. Then the electronic configuration for this one is 1s2, 1s1. For atomic number 2 we have helium, electronic configuration 1s2. For the further elements, to write, before writing this further configuration, we can use this 1s2 as the configuration of the helium. So, with atomic number 3, the element lithium, we can write either as 1s2, 2s1, or we can also write this as helium 2s1. Usually the configuration of the noble gas is written in the square bracket to indicate the inner configuration. Atomic number 4, it is beryllium. So we have this helium 2s2. Remember, beryllium cannot be used because it is not a noble gas for writing the further electronic configuration. 5 boron helium 2s2 2p1. 6 carbon helium, we have 2s2 2p2. Here 2p2 corresponds to two unpaired electrons, px1, py1, not 2px2, according to that Pauli's exclusion principle and Hund's rule of maximum multiplicity. Then atomic number 7, nitrogen. We have this helium 2s2 2p3. All the three p orbital electrons are unpaired. Atomic number 8, oxygen, helium 2s2 2p4. Then we have this atomic number 9. Atomic number 9 is for the fluorine atom. So we can write this as helium 2s2 2p5. 10 neon. We can write this as helium 2s2 2p6. Since these two have got the electrons in the first orbit itself, these belong to first period. Then all these contain electrons in the second orbit. That's why these are considered as the second period elements. These elements are present in the second period of the periodic table. Then when you go for this 11, atomic number 11, it is sodium. For this sodium, 1s2, 2s2, 2p6, up to 10 electrons, we can write as the neon. We can write this as neon Then we have 3s1. Just see, third orbit starts getting the electron. Atomic number 12, it is magnesium. Same neon, 3s2. Atomic number 13, aluminium, neon, 3s2, 3p1. 14, silicon, neon, 3s2, 3p2. Just see, carbon 2p2, 14 silicon 3p2. That means they come under similar groups. 15, it is phosphorus. It is neon 3s2, 3p3. 16, sulfur, neon 3s2, 3p4. 17, chlorine, neon 3s2, 3p5. Then 18, argon, it is neon with 3s2, 3p6. So this whole configuration can be written as the neon argon configuration. Then with atomic number 19, we have this potassium. We can write the configuration of potassium as argon configuration with 4s1. Remember, before 3d, we are having the electron in the 4s orbital, because if you compare the n plus l values for these two, 4s and 3d, 3d will be having 3 plus 2, 5. 4s is having n plus l value 4 plus 0. So 4s is having the lower energy as compared to 3d. That's why for potassium we write argon 4s1. With 20 calcium we write argon 4s2. Since these contain the electrons in the third orbit, these are called as the third period elements. Third period elements. Now onwards, since the electron goes to 4s orbital before being filled with the 3d, these elements are called as the fourth period elements. Fourth period elements. So in the fourth period, after calcium, we get the elements belonging to 3d. That is called as the transition elements or d block elements. So we have this atomic number 21. This is actually transition elements. Elements with configurations present in the 3D. That's why it is called as the 3D or first series of transition elements. Atomic number 21, scandium. Atomic number 22, titanium. 23, vanadium. 24, chromium. 25, iron, manganese. 25, manganese. 26, iron. 27, cobalt. 28, nickel. 29, copper. 30, zinc. Okay. So these are the elements that we consider as the first transition series or the 3D. So up to this 18 we can write this as argon. Then we have to write 4s2. Then electrons are filled in the continuously 3D orbital. So for this scandium we have this argon 4s2 3d1. For this argon 4s2 3d2. For this vanadium we have argon 4s2 3d3. Now for this chromium, there is a special configuration that we can confirm by various other studies, like the colors, the number of unpaired electrons, based on that one the magnetic momentum, etc. we can use. And to study the configuration, argon, it is having 4s1 3d5. Just observe, it is 4s1 3d5, a special configuration for this chromium. It is not 4s2 3d4. Remember, it is not 3d4 4s2, it is 4s1 3d5. Number of unpaired electrons are 6. For this manganese, as usual, are gone. Then electron goes to this 4s2. Then we have this 3d5. Iron, argon, 4s2 3d6. Cobalt, argon, 4s2 3d7. Nickel, argon, 4s2 3d8. Then when you come to this copper, again there is a special configuration for this one, which we can confirm by using the oxidation states, colors exhibited by that, and it is containing the configuration the argon 4s1 3d9, sorry 3d10. It is not 4s2 3d9. It is not this one. This is the correct configuration. Then we have this zinc, argon 4s2 3d10. For this especially chromium and copper, there is a special configuration 4s1 3d5, 4s1 3d10. This we have to remember as far as the configurations of these two elements are concerned. Then you just look at, I will give you one important information to remember the outer configurations. When we start with this scandium, it is having atomic number 21. Just 4s2 3d1, 2, 1. For titanium, it is 22, 2 and 2. For vanadium, 23, 2 and 3. For manganese, 2 and 5, 25, 2 and 5. 26 iron, 2 and 6. 27 cobalt, 2 and 7. Nickel, 28, 2 and 8. But copper has 4s1 3d10, zinc has got 4s2 3d10. Up to this 28, excluding this 24, we can write the electronic configuration, outer configuration, based on the atomic number itself. 21, 2, 1, 22, 2, 2, 23, 2, 3, like that. Except for chromium, copper and zinc. So this is the configuration up to the first transition series, that is 30. Now using those three rules, we can build the configurations for the remaining other elements also. So that is not required for our topic. So we shall restrict ourselves up to